This nutshell provides GPIO coding examples. We have previously created the state and structure diagram for the turnstile, bilge pump, and stopwatch. I will now show how to convert these diagrams into C code. I will also show how we can use software to deal with switch bouncing. And if you do find this YouTube nutshell helpful, please support the channel by liking the video and subscribing. Previously, we looked at a state machine for a turnstile. The operation of the turnstile shown here. We have a barrier arm which is locked and unlocked. When a coin is deposited, the barrier arm is unlocked. The single customer can pass through, then it goes back to the locked state. Here is our state machine here, locked, coin input unlocked, barrier arm pushed, locked. The code we can see here, we use bit masking for locking and unlocking the gate, which is on port C bit 0. We have a coin input on pin H bit 4, the arm spun on pin H bit 7. We have two states, lock state and unlock state. I put state as part of the variable name, or constant actually. We come through here, main, we configure the state to be locked, and we set DDR bit 0 for output. We go through a switch and a while one, we're looking at the state shown here. So if the gate is case is locked state, the gate's locked, and then we would simply go through here and keep on repeating the switch. Now when the coin is input, then the state goes to unlock state, we break, we come out back into the switch, and now we look at the case here, unlock state, the gate is unlocked, if the arm is spun, then the state goes back to the lock state. So that's why understanding a switch and how that works is important. I have programmed this into the ATmega Pro board using the Microchip Studio, and we can see the system running. Currently the system is locked. If a coin is input into the arm, the gate is unlocked. When the arm is pushed, the gate is locked. So basically, we can simply go through these two states. The same program can be designed using a structure diagram. So we have the setup ports, lock the gate, while one loop. If the gate is locked and a coin is input, unlock the gate. If the gate is unlocked and the arm is pushed, lock the gate. Looking at the code, we have the defines to lock gate, unlock gate, port C bit 0. Coin input is on pin H bit 4, arm spun, pin H bit 7. Now here I'm checking to see if the gate is locked by reading the output. So pin C will look at the input, which is connected to the output of that port. I set bit 0 for output for DDRC. I lock the gate, while 1, if gate locked and coin input, unlock gate. If gate is unlocked and arm spun, lock gate. We can see the C code written here, and I've downloaded it to the ATmega Pro board, and we can see this in operation. So currently the gate is locked. If I spin the arm, if I put the coin in, the turnstile unlocks. If I spin the arm, the turnstile locks. So we can see the unlocking with the coin input and locking when the arm is spun. Previously, we designed a state diagram for a bilge pump. The system has a top water sensor and a bottom water sensor. The pump will turn on when the water rises above the top water sensor and will turn off when the water falls below the bottom water sensor. We can see the state diagram here, the pseudocode, the state diagram. The pump is off. The top water sensor goes on, the pump goes on. Else, if the pump is on and the water sensor is turned off, the bottom water sensor, the pump goes off. We can look at the actual code here. We define the pump on and pump off, top water sensor, bottom water sensors, and then we have two states, pump off state, pump on state. We have the data direction register C, bit 7 is set for an output, and we use a switch to control the state machine. We have the state variable in here. We have the pump off state where the pump is turned off. If the top water sensor is active, we change to the pump on state. The second case we have here, pump on state, pump is on. If the bottom water sensor is inactive, change to the pump off state. So I have programmed this in Microchip Studio, and we can see it running on the board here. This is the sensor for the bottom water state. That comes on, nothing happens. The sensor for the top water state, and now the bilge pump is on. The top water sensor, it becomes inactive, the pump is still on until the bottom sensor becomes inactive, and then the pump is off. The same bilge pump problem has now been designed using a structure diagram. We can see the structure diagram here, set up the ports, pump off, repeat forever. If the top water sensor is on, turn the pump on. If the bottom water sensor is off, turn the pump off. The code is shown here. We have the defined statements for pump on, pump off, top water sensor, bottom water sensor. We set bit 7 of port C for output. Initially the pump is off, while 1, if the top water sensor is on, turn the pump on. If the bottom water sensor is off, turn the pump off. We can see I have written that in Microchip Studio and downloaded it to the C-Ridge Mega Pro board, and we can see it running. So once again we have the low sensor on pin A0 that goes on, then the top water sensor on PA3 goes on, and the pump goes on P7. Pump's working away, the top sensor goes off, pump is still on until the bottom sensor goes off and the pump turns off. Previously, we created the state diagrams and structure diagrams for the stopwatch. The operation is, if the clock is stopped, pushing the stop start will start the clock running, else pushing the lap reset will reset the time. If the clock is running, pushing the start stop will stop the clock, else pushing the lap reset, the clock will keep counting but the display is frozen. Pushing the lap reset again will unfreeze the display. The state diagram for the stopwatch program is shown here. We have the stop, clock stop display is active, lap reset pushed, we clear the clock, go back to stop. If we're in stop and stop start is pushed, the clock is running. If we're running, stop start is pushed, we go back to stop. If we're running and the lap reset is pushed, we go to lap, clock's running, display frozen. Push lap reset again, we go back to run, clock running, display active. We can see the code shown here. We have the util delay included. We show the stop start macro code for the bit masking. We have display port, and we have the 4 states: stop, run, reset, and lap. Looking at the main code, we initialize state, we set port C for output, and then the state machine is shown in the switch statement. We've had the first stop start state, count's not incrementing. If stop start is pressed, we go and change to the run state. This, by the way, is debouncing. If lap reset is pressed, we go to the reset state, coming down to the run state. We can see in the run, we are incrementing this count and then outputting it to the display. So the count is running. If start stopped is pressed, we go back to the stop start state. If lap reset is pressed, we go to the lap state. In the reset state, we simply clear the count and then go back to the stop start. In the lap state, we then still increment the count, but we do not display it. When lap reset is pressed again, we go back to the run state. I have written the code into Microchip Studio and downloaded it into the Mega Pro board. We can see the code in operation. Currently the clock is stopped. If I push the start stop button, the count goes up. If I push the stop start button again, the count stops. If I push the lap reset, the count is reset. If I push the stop start button again, the count is working. If I push the lap reset, the count pauses. If I push lap reset again, the count goes from where the count was. Finally, I can stop the clock and reset it. The structured diagram for the stopwatch is shown. We set up the ports and we have a while one loop. We're checking for start stop pressed and for reset lap pressed. If start stop is pressed, we wait for a second start stop to be pressed. We increment the count and display. In this loop, if the reset lap is pressed, we wait for a second press. We increment the count but do not display. When the reset lap is pressed again, we hop out of that loop. And then if the start stop is pressed again, we hop out of that loop. And finally, in the while one, if the reset lap is pressed, we clear the count and display. Looking at the code generated from the structure diagram, we include the util delay for the count. We have the stop start, lap reset and display defined. We set port C for output. Then we stay in the while one loop. If stop start is pressed, we go into the while loop here. While stop start is not pressed, we increment the count and output to the display. If the lap reset is pressed, we stay in the lap reset loop where we increment the count but don't display it. And finally, if the lap reset is pressed down here, then we will reset the display. I have written the code in Microchip Studio and have downloaded it to the Mega Pro board so we can see the code in action. If I push the stop start, the count starts. If I push stop start, the count stops. If I push the lap reset, the count resets. If I push the stop start again, count increments. If I push lap reset, the count is still incrementing but the display is frozen. If I push lap reset again, display unfreezes. If I push the stop start, the count will stop and then I can reset the count. Switch bounce is caused by the mechanical properties of the switch. When the switch is activated, it can bounce between open and closed, causing the microcontroller to detect multiple presses instead of a single one. We can overcome this bouncing problem by either a hardware circuit or in software using a delay. We can see software here written for debouncing. We have our inputs button 4 to 7, and we are going to toggle these LEDs. In a while one loop, we have no debouncing on this first statement, so if button 4 is pressed, the LED 0 should toggle. The second statement, we have debouncing using a countdown. If button 5 is pressed, we toggle the LED 2. We initialize debounce time, and we will stay in this while loop decrementing debounce time until it's 0. However, if we do get a bounce and detect it, we reset the debounce time. In this one here, we are going to toggle on a button press. So if the button 6 is pressed, we toggle the LED, we have our debounce delay, then we wait for the button to be released. This example here, we are going to toggle on a button release. If button 7 is pushed, we do our debounce delay, we wait for the button to be released, and then we toggle the LED. I have written the code in Microchip Studio and downloaded it into the Mega Pro board. We can see with the first button, if I push it, it's not always consistently working correctly. That's a bounce. This is a button showing debounce. It clearly changes without any problem. If I push this button, the LED toggles, then I release. Push the button, LED toggles, I release. This button here, I push the button, nothing happens until I release. Push it again, nothing happens until I release.